Okay guys, here it's fresh off the oven. Look at the steam coming off. Just finished welding it. Tack down here and a couple welds there. A couple of welds on that, just on around it. Watch the end as I put loads down it. Now it's locked here. So that really changes this thing that its ability not to want to change shape. If it wasn't locked there, it would change shape more. It would allow it to slip both outwards. But now when you put a force here downward, in this case they're talking about a clamp force down there, but we're going to add cabling in here and we're going to crank it up, and we're going to see if this amounts to just compressing this tube, or does it amount to moving the tube. Okay, if this doesn't buckle, then it can't move the tube. It just puts compression in the tube. And the one thing they're ducking is no buckling. They're not dressing the cracks that are over here. Huge cracks. Took a little liberty there. I just took a marker and put some a mark there to indicate, to help you think of where the cracks are on this side. So when they were compressing this, when it was decompression, when it was detensioned, we saw the cracks appear. When they recompressed it, when they got compression back, these cracks were present. Now, the post-tensioning could definitely buckle at that point. Should have buckled that, but apparently it did not. Not should have. It was a high chance it would buckle it if it was once they put the load on there. But it couldn't do that. It couldn't buckle that down, because it's still tied at the canopy. There's a canopy across this. See the canopy here? There's still a canopy in a nodal area up here, and it's still tied back to here, and the triangle here still exists. The triangle from this over to there. It still exists. Now we understand that they got so far they tensioned everything back. But oddly, what are the odds that they tension everything back? And when we see the videos, the collapse videos, the images online, we see the post-tensioning tool still attached. So they were still post-tensioning at the time. Tool still attached. You're still post-tensioning. Now they tell you that they let go of the tension on it, and then it collapsed. That's what they tell you. They made it through all the cycles. One report says they were on their last cycle. Nevertheless, that caused it was a totally non-structural joint here anymore to be trying to put tension on it. And that caused this whole triangle to fail down there. But we know the beginning of this whole failure, when they detensioned, was that the cracks identified themselves. And that's because the one of the reports show that from the engineer Manuel from FIG Engineering says, yeah, that it has some deflection in the deck. And it's obviously, they didn't measure it, and there's nobody talking about deflection of how many inches or millimeters or centimeters, but it's so great that they can actually identify it without having to use any survey equipment, because none's been determined to be disclosed yet. So what I did here was it's unfair. It's an open joint. There's nothing there. There's no clamp force of the two bars that are in here. And I have it on steel, and so that's going to have no profile at all besides the steel profile. And so if anything, it would have more slippage. So I'm going to put a load down here of my weight. And we have nothing. Now, I'm not putting in the equal amount of tips for that, but we see no that it's not moving. It's not moving yet. Yet it's a standing leg. But what we know is that this joint has not been disclosed as failed. Neither is this one. That leaves us one joint. Putting a load here and totally free. It's not moving. Look, totally free. There's nothing there. It's not even attempting to move out. It's not even attempting. Let me see if I can jerk at it a bit. It's not even attempting to slide out. That's most of the angle. The loads are going to go down this angle that's more, it's higher. It's higher towards 90 degrees than this one is. So you're putting a load here. The load wants to come down here. Now I do have a load coming a clamp force coming this way. A clamp force. I didn't say it's a load as in the weight. It's a clamp force. It's internal to this. And also to number 12, the back of it. Well, part of it's internal to this at the base. So they were at the bottom one, or the bottom one when they were at their last cycle. The bottom one. So that carried that torque action. They had like a backwards and forth clamping action going on in this joint. Just trading over from out number 12 to inside the deck. Remember the post-tension bars inside this deck on this one. This has already been done. Completely 580,000 pounds of kips, whatever it is. 280,000 kips. 280 kips. 280 kips. And then this one gets 280 kips out here. And that's when they were loading. No, they were the post-tension bars close to the 1 inch. So they were finishing off the clamp force inside this one. Inside the lower one, I believe, right? I forgot that wrong. You know, just reverse it around for me. So this was, it'd be made more stable by the one they completed. And this one here is, I mean, it's got, they said 50 cycles. This is at 250 kips at the point they're adding the last 30 kips on. So it's got 250 kips in here, really tight. They say there's 280 out here. That's only a difference of 30 kips before this one gets his last 30 kips. So it's only got an imbalance of 30 kips. When the bridge fails, what they're saying that they, well, two reports says that they finished it and the other one says they didn't. Let's just go with they didn't and they were on the last cycle. That gives them 30 kips. But we have another issue going on. They jackhammered this nodal area up here, this nodal area in the background. Who knows what those chipping hammer, what fractures it sent down that concrete, what damage it did to the internal stresses, internal concrete. Sorry, choking. So now I set up and I'm going to show you how I can make this slide off. But keep in mind, when I'm showing you this, don't go, oh yeah, they're right. Don't do that, because what you'll notice is this is the deck. It didn't move. And to make this slide off, and I'll make it slide off with this clamp I'm going to put here. To make this slide off, I have to move this location here. The whole nodal area, not just a piece of it, can move downwards. The whole nodal area would have to move down, and it's all incorporated into the deck and everything else, so that's not going to happen. But let's do it anyway, just to show you that I can make it slide if I turn this clamp. Now see it slide off just a little bit? Now I can do that, but it's really deforming this shape in here now. So cracks will be present, etc. at this point. And there's no, let me release that before I permanently deform my model. So don't get carried away and say, oh, but I just want you to see that you could do it if it looked like this. But it's integral to the canopy. And we have to move, the node has to fail, which I talk about. I'm stating that the bridge deck, the bridge, everything as it's stated in one of the reports, and as I stated in the original one when I said the chamfer's indicating of the chamfer crack, which is over here. The chamfer crack that's right here in this corner, when it was open, indicates sagging in the deck, which they finally admit to in the report, saying that, well, the emails saying that it has deflection. That deflection would be opposite if it's going down. So if it's going down, you can imagine that would be a pulling up away. It's no longer clamping down, as I just showed you. It's going down, but it might have a kicking out effect too, but it's going down in the middle. And if anything, it's pulling the joint away, or it could be putting compression on there. But that's, again, because of deflection in the deck. Now, when I say could be, let me zoom in on that for you, whoop, like that. We know it's deflection in the deck separate than the canopy. The canopy held out because at this point, the crack is open. The crack is open. If they were falling together, this crack wouldn't be open. So there's a crack right here. If they were falling together, it would look more like a hinge, and it would be more open down here like a V. So this would be more hinged at the hinge point, and this would open up, exaggerating a larger V, if that was more stable. But it was not. The deck and the canopy had different rates of creep, different rates of deflection. And I bet you there's a lot of strain inside these guys, even though it's something's going on weird there. They said there's no crack. Oh yeah, they do see cracks in number 10. We see some horizontal cracks, tension cracks, which indicates, you know, that the canopy might have been holding up stronger than the deck, and we get those hairline cracks that are representative like that. That's just a thought. Don't hold me to that one. So now, as you saw it, to do that, the only way to do that is I have to isolate this by itself. I don't get a chance to isolate this. I don't get to isolate it. I don't get to move that by itself because it's connected to the canopy, connected to the nodal area. I don't get to just clamp as I did there. I don't get a chance to deflect that on its own. If I deflected that on its own as it pushed away, it would be tearing apart this rest of this canopy. So if I overlap this, I could show you. Hold on. Okay, so I've got it overlaid over the scaled model. Let's go ahead and mark this. And when I clamp it, you'll see the deflection would actually have to pull this down. Now let's go ahead and mark it over here too, so we have some locked-in reference points. Let's go ahead and do that now. Let me clamp it, and I'll pick it up in a minute after I get the clamp on. But you'll see that this will no longer have that. See that hairline? That's why I can't get any closer. So let's see if I can get you. You can see keep that in mind. It already has some space, so don't take that as the part it's moving. I'm trying to be fair with the video, right? Okay, so now I applied the clamp. Hopefully you can see the larger gap now. Everything else is in place, and all I did was clamp, and I have this little bit of a lip over there. But remember, that little bit of lip doesn't exist. This is a chamfer in here. If it was a slide, that chamfer would start failing and buckling, and then the chamfer would also buckle up. You would find some cracks in the chamfer. We find cracks in the chamfer, but they're open cracks. They're not compressive breaking cracks. So it just doesn't stand. Their logic of the way it's failed does not stand. It's more of a hinge failure as it comes off of there because of the deck's deflection, as it was mentioned in the video. The deck's deflecting, and yes, they detension that. So remember, they detension, but in the only way they tested this, because they didn't use it in models, in computer modeling, is that Denny Pate stated that he just used the yard, and it held up in the yard for 2 weeks or whatever he stated. That therefore it stands to reason it will hold up out there in the real job by itself until they build the rest of the design, the backspan, etc., and it all lock in together. But never disclosing that it could not, never testing the system besides in the yard in the wrong capacity, because he tested in the yard with the post tensioning of number 11 and number 2 in place, and then in the field he detensioned the one thing that was that he didn't test in the yard, detensioning 11 and 2. If he did that on the yard, it would have disclosed itself, and the failure would have disclosed itself depending on how it was supported underneath. Who knows if they have it fully shimmed over there at the yard? That might have also been a factor that made the bridge look like it could work still. We will never know. So again, this deflection, this joint didn't fail, neither did this joint. Meaning, if it has no ability to move, that joint is a cold joint. It's locked in with post tensioning here ×4, 2 in here. It's got rebar. We know in the bridge collapse it broke back here. It didn't break at the joint. We know in the bridge collapse it didn't break here. It broke about here. So we know that this nodal area here and the nodal area here were structurally sound. So it's BS to say that that's any movement in there. With that said, remember I said the jackhammering could have caused some stress. It could have still. And when they post tensioning, they could be getting different readings. The clamp force, everything else could have changed. They now changed the elongation of the damn thing, and maybe they upped it. Maybe it's damn near 300 kips and 600,000 pounds of force down here. Who knows? That thing was just jackhammered at. We don't know the details on that. They didn't ask. So far, I have found no detail about them sharing the length, the remarks on the bar from OSHA report. From the NTSB report, they don't talk about the bar length, that they measured it, where it was necking, where it failed. They talk about nothing of stuff that would really count. Again, by itself, I can put a load up here, and I'm not getting this fancy slide yet without deflecting this area here. To slide here, you've got to deflect this. Deflecting this, deflects the deck. That doesn't slide on its own. Not on its own. All right, guys, I'll do more videos of this. I think I'm gonna put a not right now. I'm still kind of sickly here. I'm gonna put a cable inside here and clamp down for it for you. And I use the clamp. That's kind of unfair to use the clamp. The cable would be one out here, and then another one out here. The cable, 2 cables, and clamping it. I have to figure out what's the how to figure out my equal clamp force on it. They were equal, so I can apply equal clamp force and in cycles to see if I can get this to move from cycle 1 2 1 2 1 2. If I can get it to cycle like that, that'd be nice. But the whole thing is just academic waste of time, really, because that crack, they put, 560,000 pounds of force on this, and this is all already damaged and cracked up, this whole area down here. That was just stupid. It probably did fail from down there, but they don't talk about the buckling from the compressor forces. They just say this is perfectly okay. So you saw me do that clamp force there with this clamp. Now imagine if I would have cut this all, if it was concrete, and I were to break it diagonally and put the rest of the brakes in here. Because there are more brakes in this thing. It's like, it's like a mapping of brakes. If I start putting more brakes in this thing, and then I go to clamp it, if this is concrete, this is just going to fail. It's nothing there. So if anything, their post-tensioning caused it to fail. But, Denny Pate's not going to admit to that. And no one's going to admit to it. Not even the OSHA and that's NTSB report. Because as I stated in the video, and I give you links there, NTSB's been lobbied. You can now lobby NTSB if you're under investigation by them. Just give them $120,000 plus, and they'll make sure to give you a soft report that leaves everybody going, yeah, maybe it's that, and maybe it's this one, maybe it's that. But they won't address the facts. This crack here, and yet they consider themselves crack experts, with the metal fatigue. And yet we got nothing here. Take care, guys. I'm triggered, right?